Can everybody hear me? Awesome. So thank you for coming to my presentation today. My name is Vandegriend. I'm a software test manager for a company called Microsemi. Just a little bit about myself before we get into the presentation. I've been in this industry for over 15 years. I started off actually in hardware verification, testing ASICs prior to manufacturing. And in the last 4 years, I've moved more into a software test role where I was helping to verify device drivers for these ASICs. I've been using Jenkins for the past 3 to 4 years, and my talk today is really about how we integrated a software tool called LSF, or Load Sharing Facility, into Jenkins, and how that helped us to achieve continuous delivery and very quick, rapid delivery of device drivers to our customers. So before I get started, how many of you have heard of LSF before? Okay, great. So a couple of you. So the problem that I'm really addressing today is how to dynamically allocate hardware evaluation boards, or think of them as just servers. So how do we allocate servers across developers, testers, and Jenkins in order to simplify resource sharing and also to increase our throughput for automated regression testing? So LSF is a tool that was acquired by IBM, and it's basically often used in very high performance computing infrastructures or data centers. It basically allows you to distribute jobs or tests across a large number of servers, and it takes care of the dispatching, the scheduling, the resource management, and it's a very effective tool. And originally we've been using this tool for on the hardware side, where we would basically run a large number of simulations on the computer chip before manufacturing, and we were able to distribute a large number of simulations and tests across our data center, which had hundreds of CPUs. And so when it came into a software test role within our group, I introduced the concept of using LSF with Jenkins and how that helped. And that definitely helped us with our continuous delivery. So I have a few things I want to talk about today. I'll give you an overview of our build and test environment so you have some context for how our solution applies. I'll talk about the old method that we used, and then I'll talk about the new method that we use today. I'll provide a little bit of background about LSF, so you have some understanding of how the tool can fit into the problem space. And then I'll illustrate how we integrated LSF into Jenkins. And then over the past couple of years, I've been learning and gaining knowledge about the system, and I have a couple of tips I want to share with you today about how to increase the reliability and the throughput of our test infrastructure. And then finally, I'll conclude by talking about the benefits that we realized with such an approach. So even though my presentation talks about hardware evaluation boards, if you're looking to parallelize a large number of tests within a Jenkins job, this solution is also applicable, right? So I hope you can draw some parallels away from my presentation into your particular environment. So as a background, our group within Microsemi, we're responsible for developing, testing, and deploying device driver software specifically for computer chips called system on the chip, or SoCs, and these are used for optical networking, and they have multiple 100 gigabit per second ports. So very high speed chips that are used in today's networks. So we do use the cloud-based Jenkins platform to continuously build and test our device drivers. We have one master and 2 slaves, so a fairly small setup with about 25 executors, and we ship production releases every 2 to 3 weeks with this system. And the whole process is automated with one step of actually posting the device driver to the web portal, and that's done manually, and that's part of the approval step at the end. Our device driver is fairly low level, it's written in C, has about 150,000 lines of code, and the testing is done using lab-based evaluation boards. So in our lab we have about 25 boards. You see the picture up on the screen. The board has an Intel-based Common Express module, which connects to the board. It's connected over PCI Express to 3 of our chips or devices. The middle one is typically our device under test, and then the other 2 devices on the outside basically drive traffic into the middle chip. And so basically this is the platform that we use for all our automated testing with the device driver, and it's quite effective. Now to the outside world, to Jenkins and to LSF, it just looks like an LSF or a Linux server, right? Because we run Linux on the Intel-based Common Express. But really there's the customized hardware on the board, which is, like I said, connected over PCI Express. Now, in Jenkins, we have about 500 automated tests, and they take about 200 board hours to run. So if we have 10 boards, it would take 20 hours. If we have 20 boards, it would take 10 hours, right? So you can see how we very much want to optimize the system so that within the course of 8 hours, or the night, we can effectively run through all our regression tests. So this is the old method that we used for sharing boards across both users and across Jenkins. So we had 4 sites with about 50 engineers across those 4 sites. And we had a software lab in our Vancouver, Canada office, which is where I'm from. And the boards were allocated to users on a manual basis. So we had a spreadsheet or a table that we used. It kind of indicated who had which board. Most of the boards were shared across a couple of developers and testers. And then with Jenkins, we would basically manually allocate a board to a Jenkins job. And we would use the throttling mechanism to basically restrict access, because only one user can use the board at any given time, right? It doesn't support concurrent tests or well, it supports concurrent users, doesn't support concurrent tests because they tend to conflict. There's a lot of problems with this approach. First of all, if somebody's not using their board, it's really hard for other users to know that and to kind of make use of that. And then if an engineer is really busy and their board is being used by their colleague, they kind of hunt around for a free board, right, or a free server. And also our Jenkins or our software regressions, they can't take advantage of the idle boards. So at night when the developers are at home, we have no way of allocating those boards to the Jenkins jobs, right? So with my background in LSF from my hardware days, I knew this would be a good fit into our particular environment. And so just to kind of highlight how it works, is that both users and the jobs in Jenkins can submit tests to LSF, right? So LSF is basically a command line tool where basically you can take any command and you basically append it with a command for running it through LSF, and I'll show you that in a few minutes. So a user submits their test to a queue, and there's multiple queues, right? High priority queues, low priority queues, and then LSF will basically take their test or their X-term or their program, and it'll basically allocate it to a free board. And when you request a board through LSF, you can provide constraints. So you can say, I want a board with 3 devices, or I want a board that has an i5 processor. So you can request resource constraints, which LSF will honor. Then basically, when the board becomes free, or when the test finishes, the board becomes free, and then LSF dispatches that board to a new test. And then finally, Jenkins is able to make use of idle boards by using a lower priority queue, right? So essentially their Russians are filling in the slots, the empty slots during the day, and then at night, they're able to take advantage of all the boards in the system. So we realized a number of advantages with such an approach. First of all, it simplified the user experience. So they don't have to hunt around and try to find a board. They simply can just request one from the system, and one is granted to them within minutes. Also, we have a higher reliability from the system. So if we have a problematic board or a problematic server, we can simply just take it offline, and LSF will redirect the jobs to the working boards, right? And it's also more scalable because if we add boards, they suddenly become dispatched to the next set of tests that need to get run. And then finally, because we're able to allow Jenkins to access more of the boards, we were able to reduce regression cycle times and increase our ability to deliver software faster. So I wanted to compare two different types of solutions. And I saw a presentation from a couple of years ago that talked about using, running a Jenkins slave on a board, right? As opposed to treating the board as an LSF resource. So I wanted to kind of compare the two approaches because you can certainly basically treat a board as a Jenkins slave and then allocate a Jenkins job to that slave, right? Now, there's a couple of disadvantages. If the board crashes, you essentially lose your Jenkins slave, and all the tests that were assigned to it also are lost, right? In LSF, if a board crashes, you just lose that test, right? You don't lose the job. The job is basically dispatching all the tests to LSF. Also, if you use a board as a Jenkins slave, you have to worry about trying to split up your test set or your list of tests somewhat equally across a number of jobs, right? Because in this case, I have 10 slaves, right? And I have 400 tests. So I could have, 10 jobs, each running 40 tests, and I could try to achieve some sort of parallelism with that, right? But it's fairly tedious, it's fairly manual, it's not dynamic at all. With LSF, you don't really care. You can have one Jenkins job that basically dispatches 400 tests to LSF, and then LSF will simply start broadcasting them to all the free boards, right? So it's a lot simpler to basically allocate the tests across the boards dynamically. Also, if you use the Jenkins, if you run a Jenkins slave on the boards, you're now kind of creating two pools of boards. You got one pool that's used by Jenkins, you got one pool that is being used by users, and you can't really take advantage of the combined capacity, right? So it's more effective to actually have one single cluster, right, and have a tool like LSF able to dispatch jobs or dispatch boards across both users and also across Jenkins. So I wanted to talk about some of the prerequisites and some of the key points with being successful with LSF. First of all, LSF simply sees the board as a Linux server, right? So it doesn't really understand that there's customized hardware behind the scenes. I believe LSF also supports Windows, but I don't really have much experience on that front. The other thing that helps too is if all your hardware resources or all your hardware boards are fairly homogeneous in nature, then you have a much larger pool. Once you start having very specialized boards, one might have a specialized tester connected to it, or another board might have a probe connected to it. Once you start having a lot of specialized boards, you create a lot of fragmentation in your pool, and it's very hard to start gaining efficiency from having a much larger set. But I do like to point out that LSF can very easily handle specialized resources, right? And I'll show you in a couple slides how you can specify resource constraints. So we did things like, for our computer chip, we ensured that we had software overrides for any hardware fuses, right? So instead of having our chips with the fuses blown and forcing them into a specific variant, we had the ability to control that with software so that basically the chip was generic and we could basically control its mode at runtime. From a team perspective, there's a couple of important points for successful adoption. Essentially, what ends up happening is that when a user launches an extern or a remote desktop to a particular board, they own that board for the lifetime of the job, right? So if they don't close their session once they're done with it, then the board will still be allocated to them. But we use timeouts, which are enforced by LSF. So if a developer goes home, doesn't close their session, then eventually the timeout will kick in and kill their board or kill their program and return the board back into the LSF pool. So I have a couple slides just to explain some of the core concepts with regards to LSF, just so you have a bit more context behind our particular solution. So the boards or the servers are combined and put into what is called a cluster. And for each of the boards, you can essentially assign attributes to them, right? And the attributes could be essentially anything. It could be Boolean fields, it could be integers. So in the case of this first board here, I said that basically it has 3 devices. There's a Greenhills debugger probe connected to it. It has an Atom processor. For the second board, it's belonging to a different project, and it has only 2 devices. And so when you request a board, you can actually optionally request specific resource attributes, right? Or you can just leave it blank and it's a don't care. Now when you submit jobs to LSF or submit tests to LSF, you specify the queue. And the queue, typically in most setups you have something like a short normal queue and a long queue. So a short queue has the highest priority, but it has only a job limit of 1, so 1 job or 1 test per user, and typically has a timeout of 1 hour, right? The long queue, on the other hand, allows up to 10 or 20 simultaneous tests for each user, but it has the lowest priority, right? So basically, typically Jenkins would be using the long queue for regressions. And if users need to do critical debug, then they would actually use the short queue or perhaps the normal queue. So LSF has a fairly sophisticated algorithm that controls how the requests are dispatched to the free boards. It's a priority-based fair share algorithm. So essentially how it works is the more you use a board or the more you use the system, the lower your effective priority becomes, right? So it starts to penalize those heavy users, but you can weight it as well. So the system is actually quite flexible, but it does work quite well out of the box. So it wouldn't be a presentation without some command line examples. So I wanted to kind of give you a feel for how it actually works on the command line. So this first line is illustrating how to execute a command through LSF. In this particular case, I'm specifying the short queue with the -q option. The -r option is basically the attributes that, or the type of board I'm requesting. So I'm requesting a board from project 1. And basically you can see a very simple Unix command, echo hello world, right? So within seconds, the job is dispatched to LSF. And within a minute, it gets allocated to a board, in this case 105. And then since this is an interactive job, you can see the results on the screen. So you can submit both interactive jobs, like an extern or remote desktop, or you can submit batch jobs like a test executable. Just as a side note, the system is actually very robust. I took a look, and over the past 3 years, I think we submitted over 1.5 million tests to LSF. So without any issues. So it is a highly reliable system. The next couple examples show more specific resource requests. So here I'm basically requesting a board from project 1 with an i5 CPU, an Intel-based CPU, and I want 2 more devices on that board. And then the next request is basically I'm requesting a specific board as well. So a lot of flexibility in how you actually request a resource. And then there's a lot of status type functions provided by LSF. So you can view your job status with the vjobs command, and it shows that I'm currently running an xterm on a particular board. The bqueues command basically shows you a list of all the queues. It shows you the job limit per user, the number of jobs that are running, the number that are pending, that are waiting to get run. So it's a very easy way of seeing the loading on the system, right? vhosts provides a list of the host status. So you can see here that board 105 is closed because it is full, right? It has one job running on it, and it can only tolerate one job at a time. We also have our build server in LSF as well too, and basically we can allow up to 4 jobs on it. And then you see board 106 is unavailable. Typically that means that that board is not reachable by LSF. It's down. And we use this reporting as a way to automatically power cycle it. And I'll talk about how we achieve that. And then finally, there's administration, a lot of administration you can do within LSF. This gives you a different printout of your hosts. So it tells you, the amount of memory, the amount of swap space, what resources are applied to it. And then of course you can take boards offline, you can bring boards online, and you can stop and kill specific jobs. When we get a new board, it's actually very quick to add it into LSF. It's less than 5 minutes. It's basically just installing a bunch of daemons. There's typically 3 daemons that run on the board. And we modify a few configuration files that brings the board into LSF, and usually can be done within the course of a couple minutes. And like all good practices, the LSF configuration is code, or it's files which we revision control. Okay, so basically this slide talks about how we integrated LSF into Jenkins. And really, a big part of it is actually a Python script, which is simply our script for running a regression. So what this script does is it takes, we store all our tests in Jira. And so we basically extract the list of tests from Jira. We build up a test list. Now this test list contains the name of the test, and also contains how to run the test. What is the command line you need for running this test? And also contains any resource constraints that are required for this particular test. Because some tests require specific boards, and so we basically have fields in Jira which allow you to capture all this data. So the Python script basically creates the test list, and then it starts dispatching each one of the tests as a separate job to LSF, right? So it might take 200 tests, dispatches all 200 to LSF, and then LSF starts dispatching those tests to 3 boards. Now, while the tests are running, or waiting to be run, we have the script basically looks at the real-time status of the tests. So basically it scans the log files, and it also scans the job status in LSF. And it basically prints out the progress to the console, and also allows us to kill the regression if the failure rate suddenly jumps up by insane amounts, right? So sometimes we have things get into a very bad state. Hundreds of tests start failing very quickly. We want to just basically kill the regression, stop it dead in its tracks, rather than have it consume all the boards for the next couple hours. So the script basically waits until all the tests are finished, and then we then take the log files, we convert it into JUnit format, and then we have Jenkins summarize it very nicely for us. Couple nice things, or one nice thing that we did is we used the build description to basically, in the build history, we summarize the pass-fail status, just so that you get a very nice view of when you're looking at it from a higher level perspective. The next part is one of the other things that we did too, and this kind of comes down to the whole concept of making the regressions available to all the software developers, right? Because we might have, as software test engineers, we might have scripts and the ability to run regressions, but then if we don't give that ability to the developers, then they don't benefit from that, right? So what we did is we took the Python script and we wrapped it with a Jenkins job, which basically just took in a large number of attributes or parameters. So basically, a software developer could take their private workspace, submit it to this Jenkins job, and then this Jenkins job would essentially run what we call a user-based regression on their code. And so they would often do this before committing their changes to the trunk, and this helped to keep the trunk green, right? And it definitely made my life a lot easier. And so in the background, LSF is running this regression in parallel with other regressions that are going on, right? So the user is able to get feedback fairly quickly with regards to how quick or how well their code changes are working against the set of tests. So I wanted to present a few tips with regards to the experiences that I've gained over the last couple of years. One of the problems that we had is if you have hardware in a bad or corrupted state, it can very quickly kill your entire regression, right? Because what ends up happening is that if you have a bad server or a bad board, a test gets launched onto it, it fails very quickly within a second. The board is now free, takes in the next test, kills it, and the whole thing basically is a test killing machine, and pretty soon you have 100 failing tests, right? So the solution is to take the board offline as quickly as possible, and LSF does this for you, right? So what LSF does is that it monitors the job exit rate. So for instance, if it sees, and it does this by looking at the return code or the exit code coming back from the program. So if LSF sees that there's 5 failures within the course of 30 seconds, it will take the board offline, right? And it won't run any more tests, which is great. Now, on the next slide, I'll talk about how we actually then power cycle that board automatically and bring it back online. The other thing that we do to help prevent corrupted boards from killing our tests is we actually wrote a board initialization script, right? This essentially, because sometimes tests will leave the board or the hardware in some unknown state, right? And the next test comes along and it's expecting the board to be in a good state. And so this initialization script basically just does some cleanup, general cleanup, and it basically puts the board into a known good state. Now, if the board initialization fails, we conclude that that board is corrupted and should not run any tests, right? So what we do with LSF is, with LSF you have the ability to specify a pre-execution script. So this is a script that executes before the test actually starts. So if the pre-execution script fails, it returns an exit code. Then LSF doesn't use that board. It actually dispatches that test to another board. So it's a very effective way for kind of screening out bad or corrupted servers or boards prior to actually running a test on them. And then the last mechanism that we have at our disposal is that if the test if a test has a severe error, and we know that that error is most likely attributed to a bad board or board being in a bad state, we can actually fail with a specific error code, and we use exit code 99. That tells LSF to re-queue the test and actually run that test again. So that basically eliminates a set of failures due to a corrupted board. So all these techniques have really helped to improve the reliability of the system, and this definitely helps when it comes down to release time, because if you're a day away from a release date and you have 1 or 2 corrupted boards that basically kill your entire regression, you have to restart, right? So it's better to prevent the problems or to correct the problems very early on than have it kill your entire regression. So once you have a board in a bad state or a server in a bad state, what do you do with it, right? So we take it offline in LSF, prevents new tests from running on it, but we need to bring it back online. So what we do is we have a board monitoring script, and this is run periodically by Jenkins. It basically does a scan of the system. It looks at, we have system log files that collect severe error messages. If it finds a board in the corrupted state, it will first try to do a reboot on that board. Sometimes the board is not reachable. It might be completely dead. And so we use an Ethernet-based remote power switch, and we actually do a hard power cycle on it. And that brings the board back online. We actually make sure the board is operational before we return it back to the LSF pool to accept new jobs. And if the power cycle doesn't work, then I get an email, and I have to go into the lab and take care of that board. But at least I know there's a problem. The other thing that we have done is sometimes we have boards that have a manufacturing defect. And this is usually the case where the board gets reworked multiple times. We take a chip off and put it back on, and the resoldering sometimes results in a pin being flaky or not working. And then this causes a small number of tests to fail either intermittently or consistently for that particular board. So what we started to do is we started to take our sanity tests or our smoke tests, and we started to run all of those tests on the same board with 5 or 10 iterations. And then we would look at the overall pass or fail rate. And if we use the known software release, then any failures would most likely be attributed to a board issue. And then from that, we were able to create a list of golden boards in our system, and that kind of helped eliminate an additional class of false failures. Now, I know in other presentations they talked about flaky tests, and lo and behold, we suffer from that too. And flaky tests are essentially tests that can pass or fail with the same software code. And it makes it difficult to have a passing regression, right? And I found a blog article from Google. They kind of see the same problem. They're reporting, in their case, they have about 1.5% of all their tests that can report a flaky result. So of course, the ideal solution is just to fix the flaky test to make it reliable. Now, we're all limited for time, and while we strive to do that, you still have a case where you still have a small set of flaky tests. So what we do is we take our regression script and we rerun the test 3 times if it fails, right? If it failed the first time and then has passed for the 3 subsequent times, we actually modify the test result to be a skipped for the failure. But we only do that if the test is known to be flaky, right? Because what you want to avoid is you want to avoid a very stable test from failing once and then passing 3 times and then saying, okay, well that's fine, right? But if the test is known to be flaky, we want to eliminate the flaky results so we actually have results that we can more or less trust, right?
So how do you categorize it as a flaky test?
How do we categorize it as a flaky test?
What criteria?
Yes.
I actually wrote the article that he's citing up there, but
Oh, okay, great, perfect.
so the way that we detect flaky tests is we run a failing test again with the same software code, and we run it 10 times, and if it passes even once with the exact same code, then we delineate it as a flaky test. That's how we use it.
Usually,
How do we know that whether the code is not flaky? The code also may have some type of...
We don't differentiate a flaky test from whether it's in the code under test or whether it's in the test code. It could be in either place. And we found real production code bugs, and we've also found bugs in tests, the way tests are written, both. But it's still a flaky test. It's not stable with respect to the code under test, and that's the key fact.
very good discussion. The criteria that we use is a flaky test. We basically mark a test as flaky if it fails less than 5% of the time, right? So our threshold is definitely higher.
You said 5% of the time?
So it will pass 95% of the time and fail 5% of the time. If it fails more than 5% of the time, then we actually assign that, we kind of triage the failing tests, right? The tests that fail more than 5% of the time, we basically assign directly back to the developer and say, please fix your test. If it's below 5 or 10% of the time, we mark it as flaky. We still put it in our backlog of things to fix, but it often doesn't get looked at for a long period of time.
So you're saying you must record your results in a database? And
Yeah, so what we do, that's a very good question. Every time Jenkins reports results, we basically create a comma separated file of those results. So basically test name, build number, Jenkins job name. So we have a line for each test result. And then we take the comma separated file of the test results for that particular job, and we append it to a master list, right? So essentially, we have one CSV file that basically has all the test results over the last year and a half. And we use, in Excel, you can use pivot tables, you can do filtering. There's a lot of different mechanisms that you can use to look at the performance of a test, right? And whether it has passed reliably and then started to fail intermittently, or if it has always been failing intermittently. And it's not an exact science, and I wish there was an algorithm that would basically just look at our test results and say, okay, you got a problem here, no problem here, you got a problem here, right? And that would be like the holy grail, but it often involves a bit of discretion on my part and on the test engineer's part. But the rerun capability is very effective because if there's a bad code commit and a test starts to fail, normally it would only show up as one failure, right? But if you rerun it 3 times and all 3 reruns have failed, you know you've got a problem, right? Because you most likely have a new consistent test failure. So this is just an illustration of how we handle flaky tests in Jenkins. Like I said, we actually changed the fail status from fail to skip. And so here you can see that the first one failed, but it was actually, we marked it as skipped. And then the 3 after that were rerun. Now in our database, or in our CSV file that has all the test history, you would still see it as a failure. You wouldn't actually see it as a skipped, right? So, I guess to conclude, we definitely realized some benefits by adopting, LSF and integrating that into Jenkins. It eliminated the manual sharing of boards or resources, which is very tedious and inefficient. It simplified the user experience of finding a free board. Through our board initialization script, our board monitoring abilities, we have increased overall reliability of the system because we have a lot less corrupted boards that are causing false failures. By having a job that allows users to run their own regressions, we have increased the quality of the commits, and it has resulted in the regressions being more stable. And finally, with the ability to do a lot of parallelization of tests within the Jenkins job, we've been able to shorten our release cycles and get production device drivers out to customers faster. So I hope you took away a couple of interesting points, and I think we have a few minutes for questions, and I'll be around afterwards. Yes. So thank you very much for attending. I have business cards here if you'd like to grab one. Thanks again.